Yeah, thank you very much for the invitation and to let me talk here today at your workshop. So it will be in English. Sorry for that. You probably had a lot of talks about deep learning in your workshop. I mean, the last talk was about diffusion models. So this talk will be very different. It will be about the mathematical foundations of artificial superintelligence or universal artificial intelligence, how I called it a long time ago. And we have seen tremendous progress in deep learning in the last 2 years. I mean, with large language models, with chatbots, with the diffusion models, image generation, music generation, that is truly amazing. But what I have always believed is that we need a mathematical theory, or at least some formal definition of intelligence and superintelligence in order to make progress. Unfortunately, I always have to give a long introduction, and there's very little time to present the more recent work. But if you ask me, I will answer your questions, and also I will sprinkle in a few comments. For instance, how large language models, especially with chain of thought and tree of thought, can be regarded as approximations of this universal AI theory, or trying to get in closer and closer to this theoretical gold standard. But first, I have to introduce it. Will take some time. Okay. So as said, I will introduce, or the goal is to have a single agent which acts optimal in a wide range of environment. That is sort of the standard definition of AGI or ASI now. ASI stands for artificial superintelligence, and AGI stands for artificial general intelligence, not necessarily sort of superhuman. Okay. And I will present a formal definition of intelligence and also this maximally intelligent agent which can exist. Think about, if you play games like chess, you know that there is an optimal way of playing chess, namely minimax search to the end. And similarly, there's a maximal intelligent agent, although the situation is quite much more complicated than if you play a single game where you know exactly the rules of the game. Okay. So this formalizes and well defines the AI problem, which is nice. And in a sense gives a formal solution, even it's a mathematical solution to the problem, although it's not computable. So, and therefore I need to also then get to approximations. Okay, but at least it reduces the conceptual problem of AI, what is intelligence, what is artificial intelligence, to a pure computational question. Okay, and I will present some proofs and some toy experiments. Okay, so this is this theory of universal intelligence. Oops, what is this? Yes. Then I will generalize this to general Bayesian reinforcement learning, but history-based agents. Then I will discuss various variations of this agent for several reasons. And at the end, approximations and applications and more recent results. Okay. So the agent model is the standard, if you have seen similarly in, say, the Russell and Norvig AI book. You have an agent which interacts with an environment. The agent acts. The environment somehow reacts to it with some regular observation, and gives the agent occasionally a reward. +1, say, if it wins the chess, and -1 if it loses the chess game. The environment can have memory, so it's not a completely observable MDP or something like this. It's completely general, and the agent can, of course, have memory too. Okay, there's no constraint on the environment. Okay, and the specific universal agent, which are called IXI, is based on a number of principles, and I don't have time to go into these principles, but to give a brief survey, there's Occam's razor, which is the most important principle of science, or one of the most important principles, which says if you have two theories which explain your data, and intelligent agents are more about data processing, you should take the simpler theory. In machine learning, it's called regularization, right? Then there's Epicurus' principle, who says the opposite, who says well, if I have two theories which explain the data, I should keep both of them. And well, there's a contradiction between those two rules, but you can solve this contradiction, say you give a higher weight towards the more simpler theory. Okay. So an agent has beliefs and it needs to update its beliefs. And the most general way of updating beliefs is Bayes' rule. You have a prior belief, the agent has a prior belief, sees some new data, and it can update its belief. Okay, that's all fine. The question is, where does this prior come from? And we cannot just take a uniform prior or Laplace or Jeffrey's prior. There are all kinds of statistical ideas of choosing priors because they're only for very small model classes and not for general environments. Right? And in order to define a prior, we go back to Epicurus and Occam and say, well, the hypothesis or model which is simpler should have a higher prior probability. Okay. So the problem is we have to define simplicity or complexity in the most general way. And this is what Kolmogorov complexity does for us. Okay. Kolmogorov complexity, I will not give a formal definition, says the shortest program which recreates your data, and the length of it is the Kolmogorov complexity. Think about your data and you compress it with a compressor and you create a self-extracting archive. Then this self-extracting archive is a program which, if you run it, reproduces your data. Okay. And now you can think of if you have data which is very boring, like a 0, 0, 0, 0, there's a very short program which just prints 0. If you have a real data set like an image, you can still compress it, but you cannot compress it down to a very short program, right? So this compression idea captures in a universal way the information content in bit strings and then objects and then also models, okay? And well, Kolmogorov complex, I talked about programs, so we need, a concept of programs, and the universal Turing machine or the Turing machine concept in theory provides that. Okay, and Ray Solomonoff in the 60s put everything together and defined his universal prior and said the a priori belief in some model or hypothesis should be 2 to the power of minus the Kolmogorov complexity. Sorry, can you see my cursor just in case? Can you see
yes,
this little down there?
Yes.
Yes, okay, good. Anyway, I can also circle it. So this solves the prediction problem and the induction problem, which is a very old philosophical and mathematical problem. But prediction, like the language models do, is not everything, right? It seems to be a lot. You can get very far with it, but we also want to act in environments, and this environment acts back to us. This then is, chain of thought, tree of thought, RLHF, and so on, sort of in modern deep learning. Okay. Theoretically, this is done by Bellman equations. So you combine the Bellman equations, which is for planning or sequential decision making, with the Solomonoff distribution, and then you get the theory of universal AI. Okay. So formally, sorry, there's some little bit of formalism. We have a policy. An agent has a policy which maps the whole history to an action. So the agent knows the star, it's a classical star, clean star, knows the whole history of actions, observations, and rewards, and based on that produces a new action. And dually, the environment knows also the whole history and the last action of the agent and produces a new observation and a new reward. Okay. And then you measure the performance of an agent pi in environment mu by looking at the reward sum. So if an agent interacts with the environment, they create an observation action reward sequence. This is this one here, RT pi mu. And you sum from t equal 1 to infinity. There are a lot of subtleties with this infinity, but I will not go into that. And this is the total reward sum of the agent over its lifetime. And since the environment and the policy may be stochastic, you take the expectation with respect to policy and its respect to environment. And that is called the value of policy pi in environment mu. And from NDPs, you know this. But here it is completely general and history-based, no Markov assumption and so on. Okay. And then once you have this value, you just take the argmax over pi, which gives you the policy which maximizes this value. And you're done if you know in which environment the policy interacts with, which is mu. So if you know the agent plays chess, then you specify mu to be chess and maybe the opponent to be an optimal minimax player, and then p mu would be also an optimal minimax player. But that is when you know the environment. Okay. So let me go further. So now, if we don't know the environment, we take these different environments, which are these probability distributions, and calculate their Kolmogorov complexity, so how complex they are. It's K of mu, that's the complexity of environment. And we take a weighted average over all these values. Okay. So this is just a standard Bayesian thing. If you don't know your true distribution, you take a class of distribution and take a Bayesian mixture over it, in this case with this prior. Okay. And mu, so we also have to choose the class, and we want to have a very large class so that it contains the true environment. But of course, the world is very rich and very difficult, so this class needs to be truly large. So what I take here is all probability distributions, but which are computable. Okay. And in a sense, that is all we care about. I mean, you can argue that, the universe, the laws of physics are computable, or the computable environments are all the environments we can ever consider anyway. So in one sense, this class is very large. On the other hand, the nice thing is there are only countably many programs. That means this class is only countable, which is mathematically quite convenient. I can just take a sum and don't have to think about measure theory too much. Okay. And this gives you the so-called universal value or universal intelligence. So this is the performance of agent pi averaged over all possible environments weighted by their complexity. Okay. And again, you can argue, and Shane Legg, the co-founder of DeepMind, has a whole PhD thesis in a book about this intelligence measure. I will not talk too much about it, that this is a reasonable measure of intelligence. Okay. And it has a lot of properties, and sort of here give a short list which you want from intelligence measure. So it's wide ranging, it's informative, it can deal with interactive or dynamic problems. It is not anthropocentric, and it's fully defined. There's no sort of framework where there misses piecing and so on. So if you trust that this is a good measure of intelligence, well, then we take, as before, the argmax over pi, and we should get then the most intelligent agent, which I call IXI. Okay, so that is all very abstract, but you can write it down in a more explicit form. So if I plug in sort of the math here and fiddle out what this value, remember on the previous slide, this value was this expectation over this infinite sum over policy environment. So if I write that out more explicitly, it looks like this. Okay. So what is this? So think about chess, and you play the minimax optimal strategy. So you do this minimax tree, min, max, min, max, min, max. Okay. In general, you don't have an opponent, but you have a stochastic environment. So instead of the minimization, you do expectations. So instead of min max, you have expectimax. So the maximizations over actions, that's what the agent does. And then it takes expectations. The expectation is always some probability of x, f of x. So these expectations are these sums. Okay. And you do that is max sum, max sum, max sum, like minimax. Okay. So, but what is the objective? Well, the objective is to maximize reward sum. And here, for simplicity, I use a finite lifetime of the agent because, limits are always tricky, times the probability of this future happening. But we do not know the true distribution, so we have to replace it, and replace it by the so-called Solomonov distribution. So this is this last term here. I give a short interpretation. So what it does, it looks for all, and in this case, I limit myself to deterministic world models. I get back to that in a second, which describe the interaction of agent and environment. So assume the agent acts with a certain sequence of action. Then this model P This environment P produces a certain observation reward sequence. And it needs to be consistent with what we already know. So the agent is at time K. So up to K minus 1 we have observed. So this is a real constraint, O1 to OR minus 1. These are given. So we only consider models which are consistent with our data. Okay, so all programs P which are consistent with the data. But the future is sort of flexible, but we fix one future. This is one future. And we ask how, so before I said 2 to the minus the Kolmogorov complexity of the program, but the length in this case does as well. Then there are, of course, many solutions, many models which are consistent with your data. So you average over them. This is this final sum here, okay? And then, as I said, you average over all possible futures here. Okay, that's a big mess here now. And that's it. And the first max you replace by an argmax, and you get the optimal action of the IXI model at time K. Then afterwards, it observes OK and RK, and cycle K plus 1 starts, and you use the same equation again. Okay. So if you trust this intelligence measure, then this is the most intelligent agent in an arbitrary unknown environment. And again, I don't have time how to, to provide all the evidence, the intuitive evidence. I provide some theorems. So the intuition is that over time, programs P get ruled out based on the data. Many, many more programs are not consistent with the history, and only these programs which are consistent with your data survive, which gives then a good average model. And then you just do this expectimax planning. Okay. Okay. So here's a list. You can view this list in two ways: either a list of, or a partial list of aspects of intelligence, what we usually associate with intelligence, or you can think about RL, and if you know RL, there are a lot of problems which have to be overcome if you use simple models, and how the different components in this IXI model overcome this problem. So for instance, the Kolmogorov complexity takes care of generalization, associative learning, transfer learning, knowledge representation, abstraction, similarity. There's a great paper about the universal similarity matrix from Vitani and Cilibrasi, regularization, bias and variance. So all these problems which we have in machine learning are solved implicitly by Kolmogorov complexity. Okay, so that is truly magic. Okay, Bayes solves the exploration problem with a caveat which I'll come back to later. It does the learning for us, right? I mean, sort of Bayesian learning has the so if you think about classical RL, right? Bellman equations, temporal difference learning, Q learning, and more modern algorithms. So there are lots of algorithms, but none of them is theoretically optimal. They're all heuristic. They all work, some provably in limited environments. They have only asymptotic guarantees, but Bayes also has the optimal convergence rate in a certain sense. Okay. Finally, we don't make this MDP assumption. That's the reason for the history-based framework. So it solves the partial observability problem. It can deal with non-stationary environment. It has long-term memory, has large, even infinite state space. So this is all no problem in this framework. Okay. And this is expectimax, which I mentioned before, this max sum, does the planning for you. That's rather straightforward and obvious. Okay. Okay. So now I want to look at this model a little bit in more detail. And so there are lots of problems you could try to apply it, very concrete problem or problem classes. For instance, you could try to use it for sequence prediction, or for playing games, or for solving optimization problems. Or, there's also supervised learning and unsupervised learning out there. You could ask, this is a reinforcement learner. Can it learn supervised? Can it learn to listen to a teacher? And to be short, the answer is all yes. This IXI model will quickly learn to behave well in all these environments. Okay. You can also ask a lot of curious philosophical or social questions, and you can formalize them mathematically, and you can, have then, theorems rather than just philosophical papers. So one question is, where do the rewards come from? And I'll get back to that later. You can ask funny questions like, will IXE take drugs, which is now called the wire heading problem, or the hacking of the reward system, which has been addressed in this paper. We can even ask, will a super intelligence commit suicide? So we have, two definitions of suicide, and then prove theorems about it, under which circumstances. And the answer is rather natural. If you punish the model too much, give it too much negative reward, then it's inclined to commit suicide. And if you give it positive reward, then not, which can be converted, by the way, into a safety feature. So that's in this paper. A Bayesian agent explores, and exploration can be dangerous. And so this is this expression, curiosity killed the cat, and maybe also IXE. So this has been considered in a couple of papers. I've limited here IXE to a finite horizon M for multiple reasons. One is the mathematical reason, but there's also an agent reason. So immortality can make you lazy. Think about it. If you're immortal, right, why study or work so hard? You can just take everything on a slow speed. And will this model try to self-preserve, or does that have to be built in from the start? So these are all some, I would say, some curious questions which you can formalize and prove theorems about that. So that's the important thing. Now we have a mathematical theory, so we can prove theorems about superintelligence, although we do not have yet a practical superintelligence. Okay. Let me now generalize that a little bit to the stochastic case. So before it was a deterministic environment, but implicitly the stochastic environments are included. So what you do is you have here this stochastic environment sigma. Due to time reason, I have to skip over the. I also introduce discounting, so this gamma m's. So then I can take the limit easily. I normalize the value function so that it's between 0 and 1. So this one now is the value of policy P in stochastic environment sigma at time k with discount gamma. Okay, and you can again use the argmax to get to the optimal policy environment sigma. So the question is, how do we choose sigma? And well, Bayes tells us we take a class of environments M and take a Bayesian mixture over it. So these nus are all in M. This is the prior belief in environment, which is then later 2 to the minus Kolmogorov complexity. And then you get this Bayesian mixture psi, and you replace this sigma here by psi, and you get a Bayes optimal agent. Okay. So you can now ask, again, a lot of questions. So if we choose the most general class, namely all stochastic computable environments, and we choose the weights are here, which is this one, and we choose 2 to the minus Kolmogorov complexity, we get back again the IXE model as before. But now we have more flexibility. We can choose different classes M, smaller classes, which are more practical, or even larger classes. And there's, in a multi-agent setup, and we have realized a slightly larger class gives you theorems, and it converges to Nash equilibria in this thing. And the most classical results is, of course, does the value of IXE in the true environment converge to the value of the optimal informed policy, which knows the environment in advance? It's like a regret or redundancy. Okay, and so here are some results. So first, you can show that the Bayes mixture converges to the true distribution. So that is generally the case. So if you have a Bayesian modeling and your true environment is the class, then the Bayesian predictor converges to the truth. Okay. We have on-policy convergence. And remember, this is history-based, no structural assumptions about the environments. Bayes is also Pareto optimal, or called admissible in statistics. And finally, the core theorem is self-optimizingness, similar to asymptotic optimality. But there we have a condition. So not in all classes is IXE self-optimizing. And the reason is that there are classes where no agent can be self-optimizing. And the reason is because there can be traps. So if you have a trap and you don't know where the trap is, so the trap could be on the left side or on the right side, and you don't know which environment you are, there's no chance to avoid traps. And if you're in a trap, which means then 0 reward or lower reward, you lost all future reward or a lot of future reward, and you cannot have this convergence. So there needs to be some necessary conditions, okay? And a necessary condition is, of course, that there exists an agent which is self-optimizing. So assume we have a class M for which there exists an agent which is self-optimizing in the sense that it converges to the optimal value. This is obviously a necessary condition. The nice thing is that this necessary condition is already sufficient. That means if there exists a self-optimizing agent, then IXE is also self-optimizing. Okay, so IXE is self-optimizing if and only if it is possible at all. Okay, and so here is a slide with a class of environments where you can be self-optimizing. And roughly speaking, if your environment is ergodic, right, if there is no fatal traps, right, if you can always get out of traps, then you can be self-optimizing. That's the green environments. And then you have the red environments where you cannot be self-optimizing. The problem in real life, there are traps, right? You failed for the 3rd time your test at the university, you don't get a degree, you don't get your dream job, and so on, and your life changes forever. So it would be nice to have theorems about these more complicated environments. Of course, the results will be more limited, right? Because no agent can be self-optimizing. And that is a very difficult problem because we don't really have a good notion of optimality in these non-ergodic environments. Some notions are too strong, no agent can satisfy them. Other notions are too weak, that this is not really convincing. So that is ongoing research. Yes, so let me skip this one. Now I want to briefly come to some variations. So I asked, where do these rewards come from? And there are many answers. There are 3 fundamental answers. So if in the end you want this agent to perform a particular task, well, you specify your reward for this task, driving from A to B, and it is a hard-coded reward. If you want if you want an agent, which serves humans, then you would always think about a robot, interact with you, and you give it the carrot on the stick. Whatever it does, right, occasionally you reward it or punish it, and it will learn from this feedback. But if you want to build a universal agent, well, maybe we send it out to space and it explores universe and it should just do what it feels right to do. There are no rewards. So how do we choose the reward? And Laurent also had the idea that we should reward the agent with information gain, which means that the goal of the agent is to collect new data, okay? Explore the universe and learn as much and as fast as possible. And, learning and exploring requires, of course, build tools, maybe build rockets and so on, and self-preservation. So it implies all these other properties. So this will give a very remarkable agent, which is completely independent of us, right? We haven't specified a specific goal or too specific goal, and we don't have to constantly give the reward. So we just plug the rewards to the information gain. So how this is the posterior at time k-1, then it observes new data. This posterior updates at time k, and the more the posterior changes, the more information was in the data. So the more the agent likes it. So this gives you a reward, and then you plug it into the IXE model, and you can prove an even more general convergence result than for the IXE. Okay. So back to giving the IXE model rewards, there are some problems. You can, as I mentioned, it's not self-optimizing and not even asymptotically optimal in some classes, but you can fix that by introducing extra exploration. This is this base X algorithm. So if, and that ties nicely back to the information agent of the last slide, to the knowledge-seeking agent. So if there is a large gain, if there's a small gain in information, so there's not much information in the data, then it performs base optimal for one step. But if there's a lot of information to be gained, then the agent maximizes the information gain for a couple of steps. So it's a mixture between the information gain agent and the Bayesian agent. And you can prove general convergence result for this. And there's a similar agent which is called this INC. So this Bayes X agent is weakly asymptotically optimal, while this INC algorithm, which is quite similar, is strongly asymptotically optimal. Okay. So these are sort of hybrid agents which are not very natural. You can also do Thompson sampling, where you look at the posterior, you sample an environment for the posterior, and then you act optimal with respect to the sampled environment, and you can show that this Thompson sampling version agent of this agent is also asymptotically optimal, and this in case in the mean. So there's 3 different kinds of asymptotic optimality. So that's mean asymptotically optimal. Okay. Another variation is optimistic agents. So rather than taking a Bayesian mixture, you say the agent should believe it's in the most favorable environment possible. So we have a class of environments which are still consistent with our data, and we look for the environment which has the maximal value, and then we take the policy which maximizes this. So it's maximally optimistic, this agent, and you can show that this is also so in this case, if you have a finite class, then this agent makes only finitely many errors. So it's also asymptotically optimal. And you can generalize this to stochastic environments, to countable environments, and you can have rates of convergence. So you can generalize that to so-called laws, which is like factorized environments. And then you get bounds, which are comparable. So if you now assume that this agent is in a Markov decision problem, you get bounds for these agents which are similar to these PAC MDP bounds, which are polynomial in all the relevant quantities. But that's, a very special case then. Okay, let me now come to the approximations. There are a lot of possible, we developed a lot of possible approximations. So this Bayesian agent is a generic sort of approximation if you want to, because we can plug in any model class and environment we want to. Okay, the first approximation was this MDP IXI, where we just assume a very small MDP class and look at these 2x2 matrix games like Prisoner's Dilemma and Chicken and so on, and how it performs, and it does what it's supposed to do. The IXTL agent is a very theoretical approximation, which is sort of theoretically optimal, but practically has a huge constant, so it's not really useful. The MC-IXCTW, we'll explain in a second. Planning is expensive, and we know, we can either do Monte Carlo tree search for planning in practice, or we use Bellman equation of TD, and the self-IX is sort of a TD version of IXI. PhiMDP is a quite different approach, which avoids the planning, the expensive planning, but also avoids modeling the whole observable world, because many observations are not relevant, and you only want to model ideally what is relevant. That's an interesting also question with the large language models. They model everything, and for text, it's not so a problem because there's not much noise in text, right? They really predict the next token. But if you have images, right, you don't want a model which predicts everything but only the relevant parts. Okay. And extreme state aggregation is a version of PhiMDP, which sort of doesn't require the MDP condition anymore, although it still reduces it to an MDP problem, which is very curious. Okay, and IGGS is a JavaScript implementation where you can run various agents on toy problems. Okay, the Monte Carlo tree search IXI approximation does the following. Okay, the expected max planning is replaced by Monte Carlo tree search, and the Solomonov distribution is replaced by the so-called context tree weighting algorithm, which is an exact Bayesian mixture of a variable order Markov process. It's a very large class, but you could do that very efficiently. Okay, and the results are here for some toy problems, some grid worlds, and Pac-Man and Coon Poker over the experience here on the horizontal axis, and the normalized reward on the vertical axis, and you see they all converge to optimal behavior after a certain time, except for Pac-Man, we have to run it longer, and probably the model is also too restrictive. So here's just a diagram of the ingredients again, information theory, learning, planning, and complexity, which is then based on search and optimization and computation and knowledge representation. I haven't talked much about the interface, like vision and language and robots. So in theory, it's all bit strings in and bit strings out, and you can convert, of course, every input and output to bit strings. In practice, of course, you would have some pre-processing and post-processing. Okay, so here's a slide on recent progress. So I, each line I could give a whole talk, and you see some papers are very recent. So this one is dynamically injecting knowledge, so increasing the model class, not just decreasing it. So this is maybe sort of the most interesting one if you're interested in deep learning. So we're asking, so transformers essentially try to mimic Solomonov distribution, and we train them on log loss. And here we take this to the extreme, and we sample data from the Solomonov distribution, then train a transformer on it, and then ask to which extent can the transformer mimic Solomonov induction in context. Remember, Solomonov induction is not computable, so it's really impractical, but transformers are practical. And it works for more limited classes like CTW and PTW amazingly well. And for Solomonov, of course, we don't have the ground truth, but it also produces very interesting results. So there's a tie and a connection to modern deep learning. Another connection is the chain of thought and the tree of thought, which is like Monte Carlo tree search, which plays a big role in the IXE model. This I already mentioned. And there's another paper which, maybe that's a good introduction. How is compression related to language modeling and this theory? I also have a compression contest. You can win, well, in theory, up to €500,000 if you compress a gigabyte of data better than the state of the art. It's a human knowledge compression contest. Some people studied the geometry of this intelligence measure and the safety. So there are a couple. Let me see. Are they on the next slide? Well, there are many more papers. I don't have time to. I think I'm supposed to have 20 minutes for questions, right? 40 minutes talk, 20 minutes questions. So I should stop in 0 minutes or so. Give me a couple of minutes. So, okay, there's many more interesting stuff out there. And, here's this list of papers, and you can look at them. So, now we're getting closer to AGI. People are more interested in the safety aspect. And the nice thing about the IXE model, it is a super intelligence. We have it already, so we can ask safety questions and rigorously answer them and prove theorems about it. And this couple of works does that. Asks, not all is formal, but formal. I think most of it is formal except for the first one. Okay, you can ask various safety-related questions, formalize them mathematically, and prove results about it. Okay, so we've done a lot in this area also. Let me skip the outlook. I mean, of course, usually, lots of open problems. Maybe, actually, I have to remove this here. I mean, there's still more to do, but one question is, so most of the analysis is the IXE model in an environment. Since we don't make assumptions about the environment, of course, the environment can also contain other agents. But usually, if you have multiple agents interacting with each other in the multi-agent setting, you can ask different questions. And also, there are certain problems which the existing theory doesn't cover. Okay. And one big question, which is called the grain of truth problem, which was open for 25 years, we have solved. So is there a class such as base optimal agents in a multi-agent setting behave optimally? We have solved it a couple of years ago. So my old book was mentioned from 2005. But in March or April this year, a new book will come out. It's not a second edition; it's completely new. Contains the last 20 years, but also it's much more gentle. Has 100 pages of background introduction. Yeah, if you can wait, buy the new book. If you can't wait, buy the old book. Yes, that's the end of my talk. Yeah, I mentioned this compression price. There is a large frequently asked question page, which explains with a lot of examples why compression is prediction and why prediction is more or less AGI, and why maximal compression gives you then maximal intelligence. Okay, thank you very much for your attention.
Thank you. Thank you for your talk. So do we have some questions?
I have one question. Well, thank you, Professor Marcus Hutter, for a wonderful presentation. I just have one question. I mean, like, you can say that I'm sort of like a pessimist in terms of, saying artificial general intelligence, because, the term itself, it sounds, kind of a bit of a stretch. Yeah, but like, do you believe like artificial general intelligence is possible, especially in, let's say, domains that require like human like reasoning? Because the reason I'm saying this is because like these kind of like ChatGPT level like giant models, I don't think they're really capable of performing let's say like numerical operations or symbolic operations at a human level. They're trying to mimic it by taking sort of like a workaround of code generation, leveraging symbolic modules using code generation, not exactly solving it like the way humans do. So in that sense, can you really say that they're achieving the level of artificial general intelligence that you have explained in this lecture?
Well, I have not claimed that current large language models are
Yeah,
already AGIs.
Yeah.
So, I mean, I guess you can break down your question in two things. I mean, does it really reason internally, or does it behave like reasoning? And I mean, I would say, given the impressive progress we have made, especially in the last 2 years, there is a spark of reasoning, right? I mean, it's always, of course, it is not good as humans still in, there's always AI can never do X, right? But this number of X's gets smaller and smaller. And yes, you're right, the mathematical it cannot even add 4-digit numbers properly often. It's really terrible, but most humans are also very terrible in this domain, and it takes a lot of practice. Of course, I mean, eventually we get there, and these language models don't get there yet. And then you say, okay, yes, we can, we can use tools, right? I mean, tool use and retrieval in these language models to solve this problem. But it sounded like that you're not very happy with this. And you said humans do it differently. Yes, it looks like a human just have a big neural network and we do everything in this neural network. But we also have, a lot more structure in the human brain and modules. And the transformer is, in a sense, still a rather simplistic architecture. So if you want to solve the AGI problem in a pure way with a neural network, I agree. We believe we need better architectures. I mean, one, if we need a recurrent neural network, right? At the moment, what we're doing is chain of thought and tree of thought to get this long-term reasoning out of it, right? And probably, I would guess, maybe one or two, hopefully not more, architectural other tweaks. But it doesn't, I mean, do we really need that, right? I mean, if the important point is, I mean, I agree, the reasoning capacity is still the most limiting thing in these language models. And this needs to significantly improve in order to really have, AGI on a human level. And this, I also believe, needs to be in the neural network. I mean, if it at some point becomes to a very complicated reasoning like creating a proof. I mean, humans also use pieces of paper, right? But at least for these simple things, this needs to be in the neural network, and this is not there yet. So, I mean, at least given the progress we made, and I mean, I would have never believed that a simple transformer architecture like this gets us that far, does coding for us and these things. Yeah, you can always argue it's a stochastic parrot, and it is rather limited, and it uses a lot of pattern matching, and it looks much more impressive than it is. But honestly, I believe we will achieve AGI quite soon and we look at the model and we will think, wow, that's actually still a rather simple model. And it will be deeply disappointing that humans are also essentially mostly stochastic parrots and have a very simple model. So it will. That's my prediction. Intelligence is not as fancy as people think. But I mean, the future will tell. But the future seems to be near, and at least the trajectory at the moment is pretty good.
Thank you.
If you
Thank
want
you.
some more technical answers, I can give you, of course, some more technical
Thank
answers.
you.
But then you have the technical question.
Thank you.
Okay. Any other questions? So actually, I got a couple of questions. So the first one is, what is the connection between this UAI and AGI? So you started talking about the UAI, Universal AI, and then all of a sudden you talked about the AGI. Then what is the connection between these two? Could you elaborate a little bit more?
Yeah. I termed the expression universal AI in the year 2000, or even slightly before that, way before AGI was a term. I think AGI emerged in 2006. And universal AI refers to this very specific mathematical solution based on Solomonoff-Kolmogorov sequential decision theory. So that's a specific mathematical solution. And AGI is just generically the term for any system or research agenda trying to achieve AI, which is general. So that's the relation. So UAI is a specific mathematical version or approach to the grand goal of AGI.
Okay, then let me put it this way. So the current ChatGPT is getting better and better. So in future, someday, maybe who knows, but it's going to be really good, and it could be considered as AGI maybe one day.
Yeah.
Then that AGI has nothing to do with the UAI. Can I say that?
Oh yeah, you didn't mean the naming AGI and UAI, but the content. Yeah. Okay. Well, I'm actually quite pleased with the development in the direction. So we are training sequence models. I haven't talked about sequence prediction of Solomonoff. So if I had given a talk about Solomonoff sequence prediction, you would see the close relation between token prediction and Solomonoff induction. So what we do is we train this transformer to predict the next token. And we want to predict the next token as well as possible. And as a log loss, we use the log loss. Okay. And if we had sort of the ultimate flexible architecture, transformers are pretty good. You can think about more and more and powerful architectures, and you would train this. You get closer and closer to the Solomonoff distribution, which is the gold standard for prediction. So you can argue that developing and then training large language models is trying to achieve Solomonoff induction. Okay. So now, why do we use chain of thought and tree of thought? Because we want the agent to reason and to plan ahead, right? And this chain of thought and tree of thought is a version of Monte Carlo tree search. And Monte Carlo tree search is a statistical approximation of exact expectimax planning. So if I go back to this slide, sorry for the mess. Let me see where I can. Where was it? Here. If I go back to this slide, it looks like really whether people are aware of it or not, but I think, some people are aware of it. We're moving in the direction. So ICSI can be regarded as the theoretical gold standard. And it is nice if you have a gold standard, because you could, we didn't always have language models and a tree of thought. I mean, there were all kinds of different approaches, expert systems, knowledge bases, and normal MLPs and so on. So and we are getting closer and closer to this gold standard. So this last part is approximated by a transformer once it's trained, and this first part is essentially tree of thought. So at least I view it like this. And there is no guarantee that the next few ideas get us closer to the ICSI approach, but at the moment it looks like it.
Okay.
Maybe
So,
it seems. I think you're not convinced, right?
yeah, actually, I got a following up question here. So, why do we have to care all the environment? So, in the traditional RL kind of framework, so we consider just one environment, but it can solve all the problem. Not all, but it can solve the problem. But why do we have to care all the environments? So
Well,
in
I mean,
UAI,
we don't. I mean, in RL also you care about multiple environments, right? I mean, take a self-driving car or something like this, or something, maybe inverted helicopter flight or something. There's multiple environments, right? There can be wind and there can be traffic and so on. So it's still a class of environments, right? But probably what you mean is, why do we have to take the class of environments which contains, air flight and traffic and playing games and so on? But maybe you say, yes, of course. I mean, okay, is your question, why do we want to develop a single agent performing well in a lot of tasks, like playing chess and driving a car, and we could just have two different agents? Or is your question about really taking all environments?
all environment, I mean.
Okay, so if you can give me a constraint on the environment which is guaranteed to be true, I'm happy to make this class smaller. But what do we know, right? Okay, we have the laws of physics, right? But the problem is it doesn't help us much, because the universe evolved over a long period of time. Earth is a very rich environment, and even if I put the laws of physics as a constraint in the agent, it still doesn't tell me how the trees look like, right? And how leaves form and all these kinds of things. So maybe you say, maybe the world always has objects with relations to each other, okay? This seems to be a fundamental truth, right? But how do I formalize that? It's definitely not an MDP. It's definitely not ergodic. It's definitely not finite state, right? So what is the smallest class where I can be pretty confident that my true environment, and that's the important thing, I need to start with a class which contains the true environment, right? Because otherwise it will fail. And the class of all stochastic environments without any restrictions on the historic dependency seems to do the job. Yeah. So it's sort of out of necessity. Of course, if I create an agent and I have a perfect description of my world around me, then of course I don't need this framework. So for instance, if I play chess, I know the rules of the game. It's not actually true, but I can assume that my opponent is a minimax optimal player, which is a good assumption. And then I only need to care about a single environment. But that's not what AGI is about, right? Still not convinced, okay?
Yeah, thank you. I understand what you mean, but still.
Yeah, tell me a smaller class which still contains everything which I'm interested in.
I think we need we can get more kind of questions from others.
Yeah, sure.
Yeah.
Okay,
Thank you for the answer. Yeah.
Okay, may I ask a very specific question? Can you please show page 22?
Yes.
Okay, I'm curious about the reward function. the goal is to acquiring as much knowledge as possible, but you defined its reward by the KL divergence between WK and WK minus 1.
Yes.
Okay, I agree that if the agent gets more knowledge, the difference between WK and WK minus 1 should increase. But I think there should be some consideration of direction. For example, WK minus 1 is carrying some amount of knowledge, but losing the whole knowledge can increase the KL divergence. Therefore, don't we have to think about the direction of the movement or change?
Well, I mean, first, it's the base rule, which is the optimal update rule for information. And it's a very good question. But if you have, and the Bayesian agent never sort of forgets in the human sense. So the only way to lose information is if the previous information was inconsistent, right? So assume I've observed a lot of ones, right? And I believe, oh, maybe it's always one. And then it starts to maybe become random 0, 1, 0, 1, 0, 1. So this was just a statistical fluke at the beginning. But that still means I have learned something, right? So the things which I knew at time k minus 1 were apparently a statistical fluke, right? And new data shows me that the structure I found, agent found at time k minus 1 is actually not true structure, but it was due to random noise, and I have to unlearn it. But this is still valuable information, right? So if you see some pattern, you see the tiger in the bush, right? But then you look just once more and the pattern vanishes, that was still quite useful information. Yeah. This informal argument is maybe not convincing, but the math turns out to work. So sorry, that's the best explanation I have.
Okay, thank you for the answer.
You're welcome.
Thank you. And time's already up. Do we have any other questions? Okay, then I think it's time to close the talk. Okay, and actually we learned a lot. Thank you. Thank you, Professor Potter. Thank you.
Thank you very much for the invitation. 안녕히 가세요.
Thank you.
Thank you so much for the valuable lecture. It was really interesting.
Yeah, thank you too. Good luck with the remainder of your workshop. Thank you very much for the invitation.
Thank you.
It was a pleasure.
Thank you. Bye. 오케이, 그러면은 제가 마이크를 마지막 그 단장님인 김민준 교수님께 마이크를 넘기고 저는 물러가겠습니다.
네, 이렇게 해서 저희가 준비한 강의가 모두 마쳤는데요. 긴 시간 이렇게 많은 분들이 참여해 주셔서 열심히 들어주셔서 감사하고요. 그리고 이 워크숍이 원래 저희 한동대에서 주최를 할 때 저희 BK21 사업단이 특별히 그 산업 혁신을 위한 산업 혁신에 공헌하는 것을 이제 모토로 좀 삼고 있는데 이러한 관점에서 회사에 계신 분들에게 좀 도움이 많이 될 수 있는 그러한 내용으로 많이 준비를 했고요. 그리고 가능하면 최근에 좀 이슈가 많이 되고 있는 주제들을 다룰 수 있도록 그렇게 좀 준비를 해봤습니다. 참석해 주신 모든 분들께 도움이 많이 됐으면은 좀 좋았겠고요. 그리고 내년에도 또 개최를 할 텐데 관심 많이 가져주시고 또 많이 참여해 주시길 바라겠습니다. 그럼 대단히 감사합니다.
수고하셨습니다.
수고하셨습니다.